Good morning, good afternoon, people of Earth, and welcome to our Spacebook Live. Today we are going to talk about exoplanets, and for this Spacebook Live, I invited a very special guest, a colleague of mine for various years, Jason Wang. Hi, Jason.
Hi, Frank. Thanks for having me.
So Jason is Ising Simons Foundation 51 Pegasi B Fellow. He works at Caltech University. Not too far away from us in nearby Los Angeles in Pasadena. So today I invited Jason to talk about exoplanets. But before that, I just want to make sure that everybody knows that you should tell us where you are located, where you are watching this Facebook Live from. And of course, you should know that you can ask us questions. We're going to have a conversation first, and in 15 minutes, we will take questions from you. So feel free to write them down at the bottom of this Spacebook Live in the comment section. We will be answering to some of them, of course. So Jason, I invited you today to talk about exoplanets. We know 4,000 exoplanets, even more now. I need to change the numbers every week. So the reason I invited you to talk about exoplanet today is because you have a very special exoplanet to talk about. You led a paper that was published on May 18 about a weird system called PDS-70. So first of all, tell us a bit what you do at Caltech and why this system is particularly interesting.
Yeah, sure. So hi, everyone out there. My name is Jason. I am an astronomer at Caltech, and I study exoplanets. So those are planets orbiting other stars, and in particular, I study trying to take pictures of these planets, trying to take pictures of other worlds orbiting other stars. And I do this using some of the largest telescopes in the world, using some of the most advanced instrumentation in the world, really trying to push the bounds of using the largest telescopes we have, the most sophisticated instrumentation we have, so that we can take pictures of these really faint exoplanets up close right next to the bright host stars. And by taking pictures of them and studying them, we can actually study them directly and try to understand, what kind of planets these are and how they formed. So one of the systems that I worked on is the system that we astronomers give the very undescriptive name PDS-70. That just means it's the 70th star in some catalog titled PDS. But it's a convenient moniker for us just to refer to it by. This is an interesting star because it's a very young star. We think it's about 5 million years old. So that probably sounds like a really long time in human scales. 5 million years is like literally forever. But if you think about the geological history of the Earth, the dinosaurs went extinct about 60 million years ago. So this star was born much closer in time to us humans than dinosaurs. They're only 5 million years away from us humans, but 55 million years after the dinosaurs went extinct. So it's a really young star in terms of the universe. But what's interesting about the star is that it's the first system out of the 4,000 plus exoplanets that we know of that we can actually directly witness planets in the midst of formation. So almost all the systems that we know of are really old systems like our own solar system, in which everything has already formed, everything's settled down. We're kind of like hanging out in middle age kind of solar system. Whereas this system is a newborn system. These planets are still in the process of forming, and by studying them directly, we can try to understand how planets form.
So to observe those planetary systems, especially this one, you mentioned that you use large telescopes and cutting-edge instrumentation.
Yes.
Can you tell us a bit more about this?
Sure. Yeah. So for this specific study, we used one of the Keck telescopes. So behind me, in my background, you can see we're actually up here on the summit of Mauna Kea. Well, virtually, I'm not really on the summit of Mauna Kea. So Mauna Kea is a mountain, volcanic mountain in Hawaii. It's has this elevation of I want to say around 14,000 feet or something like that. It's really high up, and I took this picture a couple years back during sunset. So behind me are some of the largest telescopes in the world. There's the Subaru 8-meter telescope there, and over there on the right are the two. I'm trying to do my best Vanna White impression. These are the two Keck 10-meter telescopes. These are twin 10-meter telescopes. We use the Keck II telescope, which is this one, the one closest to me. So we used this telescope, one of the biggest telescopes in the world, and we used it with some new advanced instrumentation that we just installed this year that allows us to better correct for the turbulence in the atmosphere, so we can actually clearly see these planets very cleanly.
So you basically remove with this system the effect of the atmospheric turbulences, so that's allow you to get a very good image.
Yes.
But then you need to be able to see a planet which is significantly fainter, right?
Yes. Yes. So so maybe let's talk about how we take pictures of exoplanets. So I drew this little cartoon, which I like to share of how we take pictures of exoplanets. So let me just show this one slide.
In the meantime, I'm going to say that we have people from Ohio, Surrey, UK, Argentina, Holland, Texas, Richmond, Virginia, Kansas City, Titurville, Florida, Paris, France, Norway, Massachusetts, London, Port Huron, Ghana, Lancaster, Serbia, Leeds, Syracuse, Bratislava in Slovakia, and Athens in Greece. So welcome, guys. We're going to talk about adaptive optics.
Yeah, well, I'm actually from Ohio, from Columbus. So hello to the other fellow Ohioan. Yeah, so this is my little cartoon of how we actually take pictures. This is like the cartoon optical diagram. So our goal is to take pictures of these faint exoplanets, but they're up close, right next to their bright host stars. And this might be okay, but usually we have to really see them, we have to use some of the largest telescopes on Earth, and all these telescopes are on the ground. We just can't fly such a large telescope yet. We just haven't done that. It's hard engineering. So all these telescopes are on the ground. So unfortunately, the Earth's atmosphere, which protects us from the sun's harmful rays, gives us life and air and all this nice stuff, all that turbulence and weather really messes up the image quality. It completely blurs the images of these stars and planets, making them really hard to see. So what we do is basically visit our local optometrists, which in this case are these scientists, adaptive optics scientists. And they essentially give our telescope glasses, a better prescription. And normally, we go to the optometrist like once per year, or maybe once per several years if you're lazy like me sometimes, to get your eyes checked and to update your prescription. However, the Earth's atmosphere changes really fast. You might have noticed anytime you look at the sky and see stars twinkling and things like that. The Earth's atmosphere changes about every millisecond or so, actually. So we actually need to visit the optometrist every millisecond. So we have this system that we call adaptive optics, which allows us to basically change the prescription on our glasses for these telescopes every millisecond to correct for the Earth's turbulence. And with that, we're able to get this very nice, clean picture. And after we get that nice, clean picture, we're able to then try to see the planet. So one last thing we had to do is use something what we call a chronograph to block out the glare of the star. It's essentially putting a thumb in front of the star, but it's a bit fancier than that, because if you tell any astronomers that we're just using thumbs to block out the starlight, they'll probably tell you that it's a lot more complicated and there's all these optics.
They will get offended.
Like they'll get offended probably. Yes. But it's a layer. To think of it, it's kind of like this. We're putting a fancy, very fancy thumb out there to mask out the glare of the star. And then after we're able to both get these nice crisp pictures with adaptive optics, and also using this chronograph to mask out the glare of the star, we're able to take a picture of these planets with our camera behind all of this. So that's kind of our cartoon schematic. I have one slide showing the importance of adaptive optics. So here's an image of a star that we've taken. This is actually data that Franck and I took. This is with the Gemini Planet Imager, a separate instrument on another large telescope. But you can see this is actually an image of a star, and it's taken, what you're seeing is a time lapse, and each animation is about 1 second in length. So, well, each frame is about 1 second in length. So you can see these are images taken about every second or so, and you can see this is the star. It doesn't look like what you imagine a star would look like, right? It's because if you look at a star up close, through our atmosphere. It actually looks like a giant fuzzball. All this is the atmosphere blurring the star's image. But once we go to the optometrist and correct for the Earth's atmosphere, we get this really nice crisp image. So on the right here, that star that was a giant fuzzball is now a nice crisp image on the right here. And what's more is that there's actually, if you have a very sharp eye, you'll notice there's actually a second point of light. There's actually a second point of light right here. This is actually, this is not a planet, but this is actually a binary star system. This second star is about 10 times fainter than the first one. And without adaptive optics, we would have never seen the second star. It would have been completely lost in that giant fuzzball glare of the first star. So planets are somewhere about 1 million times fainter than this. So you can see why adaptive optics would be really important to distinguish the faint planet light from this glare of the star that would otherwise just be completely like drowning out the light of the planet.
So we do have the capability now to basically cancel out the effect of the atmosphere and improve the sharpness to be able to see faint objects nearby stars, like planets, like disk around planets. And we had Tom Esposito talk to us about the disk around stars discovered with GPI.
Yes.
So in your case, you applied this technology at the Keck telescope with the Keck telescope for PDS 70. So what did you see?
Right. So let's actually put the next slide. Give me a sec. So this is what we saw. So on the left is what has been previously seen. So this is an image taken by another large telescope, the Very Large Telescope, one of the 8-meter telescopes in Chile. This image here on the left, this is a previous image. It's taken in the near infrared. What that means is this slightly redder wavelengths than visible red. So some things that we can't see with our human eyes, but are still pretty close to visible light wavelengths. And here in these images, what you can see is that the star is here blocked out by our fancy thumb. There's fancy chronograph. And all this other emission is material surrounding that star. This is the disk in which planets are born. And inside that disk, you can see one point source of light. This is one of the planets. This is PDS 70b, lowercase b. That's what we call, that's how we name planets. We name them b, little c, little d for every planet we discover in a system. So this is PDS 70b. You can see it very clearly. However, there's actually a second planet system. It's actually right here. And it's really hard to see by eye, just because one of the hard things about studying these planets is that the dust disk in which they're formed looks very similar to the planets themselves. And since they're still accreting material from the dust disk, they're all connected together. So it's hard to distinguish what's a planet from what's just disk features that could be forming planets in.
So this is basically a baby sun, very young sun, which is still forming its planet around. So what you can see here, those fixtures, those structure here, those are kind of dust and gas surrounding the planet.
Yes,
and
that's
inside,
right.
You may have planets in formation, maybe a cocoon of hot planets. Is that correct?
Yeah, that's a good description of it. So that's kind of what we're seeing here. But the hard part is it's really hard to distinguish, are we seeing planets, or are we just seeing dust in which there could be planets enshrouded inside? So that's one of the hard things. So what we did was take images with Keck using this telescope right here. We took images in the thermal infrared. So this is at longer wavelengths. Here we're seeing more of the heat. And because planets, when they're accreting, are very hot, they're brighter at these longer wavelengths. So we can better see their thermal emission, their heat. But however, even at these longer wavelengths, it's still hard to distinguish, is this bright spot really another planet, or is this another, just again, part of this disk that's around the star? And what we did was come up with this technique to actually model off and subtract off the disk of the star so that we can isolate these two planets. So here on the very right, here I've subtracted off a model of the disk of the star, and here we can see isolated are these two planets, PDS 70b little b and PDS 70 little c. These are the two directly imaged protoplanets, the only two directly imaged protoplanets that we know of, in which we know that these planets are still in the process of forming, so we can use them to try to study how planets form and accrete material and grow.
Before we go deeper into this, I would like to mention we have new people who joined us from Arkansas, from Bertioga City in Brazil, Spain, Montreal, Fayetteville, North Carolina, Cantonment in Florida, Brazil, LeConte in Louisiana, and someone even further away from everybody else because it's from Arcturus in the Pleiadian system. So we're serious, but welcome to people on Earth and elsewhere. Of course, we are the SETI Institute, so we like everybody, even aliens. So so now we have a picture, thanks to adaptive optics and the Keck telescope and this new system and this data processing that you apply. We are being able to analyze, to confirm the existence of those two planets around PDS 70. So one is B, one is C, as you can show on this figure. And we now have extracted basically the flux, the light coming from those planets, right?
That's right.
So what do you know about these planets now? What do we know about those baby planets?
That's right. So these are like the first two systems. We're still in the early stages of really piecing together all the knowledge of what's exactly going on in the system. But what we think is that based on how bright these planets are at all these different wavelengths that we observed these planets at, we think that these planets are about somewhere between 1 and 4 times the mass of Jupiter. So these are pretty massive planets. These are precursors to Jupiter-like planets, like precursors to Jupiter in our own solar system. So if Jupiter was, say, only 5 million years old instead of, say, 5 billion years old, if it were 1,000 times younger, this is what kind of picture we would be seeing of our own Jupiter in our system. We also think that due to the fact of what kind of molecular features we can and cannot see in these planets' atmospheres, we think that these planets are very dusty, that the planets are still accreting so much dust from the disk that they formed in, that this dust is completely shrouding the atmospheres of this planet. So these planets are completely shrouded in the dust that they're accreting and making it hard to really see inside. However, we're still we have a few new techniques we're hoping to leverage in the future to really peer inside these planets and understand what's going on in their atmospheres, what kind of compositions these planets are made of, and what kind of planets will these planets become.
And so now we have an understanding of the structure of this system. I'm assuming now you can also do some modelization of the 3D features, so kind of have a better understanding of how the structure form as well, these weird arms around the star, and so on. So I remember I've seen picture, an artistic view of this system. Do you have that?
Yeah, let me pull that up. Oh, I'm still screen sharing. Okay.
And I remind people that they're welcome to ask any questions on the topic of related to this conversation on these 2 large exoplanets, PDS 70b and C. Go ahead, explain to us this, because this is something I've seen and I would like to know more about that.
Yeah, so this is an artist conception that, so this is something I worked with an artist on in terms of trying to make an artist conception of just like, here's qualitatively what's going on in the system. Not everything is perfectly accurate. This is not what you would see by eye. In particular, things aren't to scale. These planets and stars normally their radii are much smaller than how far separated they are. So these would essentially be point sources. Like they'll be smaller than a single pixel, basically. But to really kind of capture the different scales at work here, we've kind of enlarged some scales to kind of make you be able to see all the different scales in which things are happening. So here you can see this is the circumstellar disk. This is the reservoir material from which planets are born from. Here you can see 2 bright sources of light. These are the 2 planets, PDS 70b and C. This is its host star. And you can see that as these planets are orbiting, they're actually carving out a gap in this disk. They're basically accreting and taking in all the material that was formerly in this gap. And now all that material from this gap have accreted onto these 2 planets. But even after these planets have kind of consumed everything in their immediate neighborhood, they're still accreting. You can see there's these arms, these arms we haven't detected observationally yet, but have been predicted from simulation, are arms of material coming from the circumstellar disk, the reservoir of dust, and flowing towards these protoplanets. It's basically continuing to feed these planets' growth and letting them continue to get larger and larger and accrete more and more material.
So this will stop when basically there will be less material in the disk, or when the disk will completely disappear.
Yes, exactly. So as they accrete more and more material, these gaps are going to get bigger, so it's going to make it slower to accrete even material from even further away, and this gas will eventually all evaporate, get blown away by just the bright host star. Its luminosity will essentially evaporate a lot of this gas and dust.
So we have questions coming related to this. In fact, one question from Rebecca, who is asking if all planets form the same way. They all form from this protoplanetary disk in every system?
That's a great question. That's something we're still working on, but we think that we're starting to come to a consensus that we think that the large majority of planets formed in this way, that they formed from a protoplanetary disk. And from that disk, they accrete more and more material and grow larger and larger. The planets that grow, that accrete material efficiently, grow very large, become planets like Jupiter. The planets that don't accrete material very efficiently, or are unable to accrete material very efficiently, those become your smaller mass planets, planets like Neptune, planets like Earth. Those are planets that just didn't grow as large. There's many different reasons in physics for why that could happen. But that's the general picture of how we think most planets form. We do think that there are other possible formation channels to form kind of your planets at kind of like your weirdo planets that formed say very, very far away from the star. So these planets are about at the orbit of Neptune and Uranus. So these planets are still at the edges of our solar system in terms of, if you think about the major 8 planets. But we've discovered planets out at 10 times, 100 times that separation at 2,000 astronomical units. That's basically the edges of our own solar system. We've found planets around other stars at those distances. There, we don't think that they formed inside the disks. We just don't think these circumstellar disks that give birth to planets, we just don't think they extend out that far. We think that they must have formed through some other channel. But for the vast majority of planets, we think that they formed in a picture like this.
Great. We get, in fact, 2 questions about exactly that. So you already answered to the question from Bart. So that's great.
All right.
So this formation process that you see right now, this is the 8 million years old system, it's going to stop. What will be those planets? You said there will be gigantic planets that will stay as big as Jupiter or even bigger, or they will shrink. Do we know how they evolve over time?
So we don't have firm empirical evidence for every stage of the process, but we think based on our current knowledge of physics and what we think goes on in giant planet evolution, and just extrapolating physics through time, we think that these planets will remain somewhere between 1 to 4 Jupiter masses at the end. We think that these planets are still forming, but near the end of their formation process, that they've accumulated, say, 99% of their masses already. They're still accreting some stuff, but it's near the edge. It's like, well, they're almost done.
So we have a question from Jennifer, who is asking how we're going to find out about the composition of those planets. Do we know if they're rocky or gas giant? And how are we going to be able to see the interior composition, the atmosphere composition? Is that going to be possible in the future?
That's a great question. So we do think that there will be gas giants just because of how massive they are. We just can't come up. In the universe of all the thousands of planets we've discovered so far, we haven't seen planets this massive that aren't gas giants. And also just from our current knowledge of physics, we just can't see a way that you can make something that wouldn't just become a gas giant if you have this much mass. So we think that they'll become gas giants. What their exact compositions, what they're made out of, we're hoping to study that soon. We're developing more new instrumentation at Keck using the same telescope. We'll have some even more upgrades to allow us to better study planets. In particular, we're going to study them using what's called high resolution spectroscopy. So here, instead of just taking an image, we'll be taking spectra. So this will be trying to disentangle what all the different molecules are in these planet in the emission from these planets. So we're trying to see individual molecular lines to try to discern which molecules could exist. And even if these lines are partly veiled by the dust, we think that we might have a better chance of seeing them at these very high spectral resolutions using this new technology.
So before you remove this picture, because we like to be able to see you, we get a question, a comments question at the same time from Peter. So this is not a real picture, Peter. This is an artistic view of the system. The real picture, can you show it again, please, Jason?
Yeah, the real picture is not as cool, not as splashy, but I think just as cool, or maybe not cooler. These images here, these are all real images of the system.
Yes,
and
those are pictures. So that is basically, those are photons coming from the object that came into the instrument to create this image. We're great. Okay. Yeah, you can stop sharing this way we can see you live.
Okay, sounds good.
So I get some questions here. A question which is not a snarky question, but it's an interesting one. I like this question. Are we truly learning something new scientifically from those images? Are we learning about the formation of planets? You mentioned that. And what is the next step, basically, in this field? This is from Ron.
Yeah, it's a great question. So we're trying. So basically, right now, how in our understanding of giant planet or just planet formation in general, we have a lot of theories. However, a lot of these theories haven't been really tested yet, just because we haven't had these kind of observations. So this is kind of the first two data points in testing these theories of how giant planets form. So some of what I'm saying is these are the facts we know, and some of it is here's what we generally think is true, but all these hypotheses haven't been tested yet. And in particular, all the details for how do giant planets get this massive? How what kind of materials are they accreting? How long does this accretion process last? All these details, if you ask different astronomers, astrophysicists that are modeling these things, they will give you vastly different answers. So we're trying to adding the first couple of data points in trying to constrain them to these things. So here we see planets still accreting materials at about 5 million years old. So we know that this process isn't something super short. It doesn't take less than 1 million years. It takes a few million years for all this to happen now. And this is already helping us set up some timescales, giving us some constraints on what kind of physical processes will be important to create these planets.
Yeah, and to answer to Ron, I will say something I often say to my colleagues. There is 3 times more, 3 magnitudes more, or there is 3,000 times more theories than there is telescopes. Okay, so it's always easy to have a lot of theory and models, but at the end, to be able to see a planet and to see the interaction of a planet with the circumstellar disk, it's very difficult. It's a very difficult problem to solve. We are getting used, you and me, to see those planets, but I will say that 15 years ago, people will not believe that it will be possible to see Jupiter-sized exoplanet in orbit around stars. This is a new technology, so we just now only getting those images and the data that we constrain those models.
Yeah, and we're hoping to get more discoveries of planets like these, especially now with new upgraded technology like here at Keck. We're able to study some of these stars with adaptive optics, whereas previously we could not have, because a lot of these stars lie in very dusty star-forming regions. So not only are planets born from dusty disk reservoirs, stars are born from dusty clouds that condense and collapse and form stars. And in the visible, these clouds basically block out a lot of starlight, making it really hard for us to see these planets. so what we've done at Keck is be able to do all this in the infrared, do adaptive optics, do this correction, do all the imaging in the infrared, so we can actually see through all this dust and see these star forming regions that we couldn't really well see before.
Thank you. Well, we're gonna end here. I just would like to just ask you one final question, Jason. So what's the next step for you? You are doing this postdoc at Caltech. What's your big next project? Can you tell us a bit about what you're gonna publish soon, or what's your goal on in the next 10, 15 years?
Sure. Well, for the next project, we've gotten more and more observations of these systems. So there will be more studies of this. So you stay tuned. We're using some other really large telescopes all around the world. We've accumulated new data. We actually think we might have detected some molecular species using these planets. We're working on trying to study exactly how dust accretes onto these planets. So we have lots of new exciting avenues to study these planets and hopefully other planets like this one in the near future. So I hope you all stay tuned and hear more about how planets form.
All right. Well, thank you again. Thanks for your time. I didn't ask where you are physically right now. Are you in Pasadena or are you?
I am in Pasadena right now. I am in Pasadena.
Right.
Yes.
Great. Well, I hope to see you in person soon.
Yep.
We're supposed to see each other at least once a year, so let's try to do that this year.
Sometime, hopefully, yes.
Thank you very much to all our viewers from everywhere on this planet. People join us toward the end. It's going to be recorded. This conversation will be recorded, available on Facebook, on our Facebook account, but also on YouTube. Feel free to comment, to subscribe, to join us in this great adventure of understanding how planets form, how life appears in the universe. Thank you again, Jason. Have a good day and see you soon.
Thanks for having me. Bye, everyone.